In the last video in this lecture, we discussed the basic process for turning control theories into dynamical theories so that we can deal with more different phenomena. Then I went through a constructive process that we could use to derive the equation that I've written right here. That constructive process involved dividing our whatever system into a bunch of little chunks, little tiny boxes, and having those boxes undergo thermal joins with each other over time. This equation is called the heat equation, and we'll see that there's actually maybe another way that we can get it. This way is in some ways a lot cleaner and in some ways sort of wishy-washy. So I like the fact that we have both of them, that they can work together. What you might be nervous about from the approach from last time is that it was really specific. I came up with some very specific set of joins, some pattern of the boxes touching each other in order to come to this equation. And you might wonder if some other pattern might have led to different sort of behavior within the equation. So the answer that we'll see here is not really. This is actually basically what you have to get. And what we're going to do is approach this using symmetries. Now, some of you may have seen this in a former course, but I think it's something we often don't expose undergraduates to. Oftentimes, there are good ways to guess what differential equation we should get to describe a certain set of phenomena just based on symmetry. So what are the symmetries that we have here? Again, the model is something like an infinite line of ideal gas somehow. In the last lecture, or sorry, in the last video, we divided that line up into these little boxes. But in principle, we don't know anything about the boxes. We just have this line of ideal gas. Well, we can say a few things. The first one that I want to point out is that we have made our lives easier by letting this be an infinite line. There are certain kinds of translational symmetries that we can get when we assume that the line is infinite that we don't actually get if we assume a finite line. And so you might worry that since in the real world, we're often interested in finite objects, we really can't assume those symmetries, those translation symmetries at all. However, we often do still make these assumptions in physics because if we have something that's relatively long, then those symmetries, which are now just approximate, kind of do apply in the middle of our sample. Sometimes they're called bulk symmetries. So we're still going to allow them. We're going to assume an infinite line and not worry about the fact that that's not necessarily physical. The other thing that's very important and that we often have to do in physics is notice that a differential equation can have more symmetry than its boundary conditions. So we want to assume the symmetries that the equation should have before we say what the boundary conditions or initial values are. Okay, with all of that out of the way, let's start going. Nothing about our system changes if we shift it along. Remember, it's just a line. So it has spatial translation symmetry. Even more so, it has spatial reflection symmetry. If we flip it, the system looks exactly the same. Next, the system has time translation symmetry. Nothing happens if we sort of do the same experiment in 2 seconds or something like that. But notice that we do not have time reflection symmetry. And this is a consequence of the second law of thermodynamics. When we do the thermal joins on these little boxes that are all next to each other, that's going to have the net effect of increasing the entropy or leaving it the same. But that process then can't be done in reverse. This is one of the sort of ways that we see when we go from classical thermodynamics, which is not a theory of dynamics, to a theory of thermal flow. The second law takes on a dynamical character of not allowing time reflection symmetry. We'll talk about that more later on in the course, but this is one place where it's rearing its head already. Wonderful. We have a few more symmetries that are maybe a little bit more subtle. One of them is that the way that we've constructed the problem, we have both sides being extensive. And let's be a little bit careful here. Notice that we have extensive u here, but t and x in one dimension at least are also both going to be extensive. This is the first place we're seeing t appear, and so it's important to note that t does play the role of an extensive variable in the theory. Wonderful. So I guess actually we have extensivity of u, intensivity of the whole left-hand side. That means that d must also be extensive. This is kind of interesting to note. I guess I'll just leave extensivity here as something we need to think about. The sides should have the same extensivity as each other. And that should be preserved throughout transformations. Okay, a couple more. One is that we know that changing all of the u's, u at every point, by a constant doesn't affect the physics at all. So u of tx goes to u tx plus u naught does not change anything. And that's probably good for now. That'll give us a start. Okay, so we know that we're going to want a differential equation in the end. So let's just try writing down a differential operator. We'll have some differential operator acting on this thing u of tx, and we'll say it's equal to 0, right? Because we could just move all of the terms to one side. Okay, let's call this like script f or something like that. So script f. And there's an important point that I actually haven't made here because it's not exactly a point about symmetry, but it is something that's very important about physics, which is that often we anticipate having local operators, okay? So a local operator is only going to be determined by the value of the function in a neighborhood of a point. So the function itself, multiples of the function, those are local operators. Differential objects acting on the function, also local operators. Something that wouldn't be a local operator is if this differential equation involved u of t minus some constant, so t minus tau or something like that. That would be something called a delay differential equation, and it's something that's explicitly non-local in the time direction. Okay, so we're going to assume locality. And actually, even more than that, we're going to try to make this system as local as possible. So the system gets more and more non-local as we look at higher and higher terms in the Taylor series or something like that of u. So as we take higher derivatives. So we're going to keep that in mind as we continue. Okay, without further ado, let's keep writing things down. So we have something that could depend on u. It could depend on t derivatives of u. It could depend on x derivatives of u. It could depend on, let me just write this in words, mixed partials of both t and x. It could depend on t, and it could depend on x. And this thing will equal 0. Good. But immediately our symmetries make a couple of these things cancel out. The first one is spatial translation, means this can't depend on x. Otherwise, f would change if we changed x. If we did a spatial translation, right? So if we moved x to x plus c, f would change. And then similarly, time translation means that this can't participate in our f object. Good. Okay, the next thing that's pretty interesting, I think, is our spatial reflection symmetry. This turns out to be very important because it means that if we send x to minus x, we should get the same thing. And that ends up meaning that all of these derivatives that depend on x have to have even order. Because if we had dx by itself, for instance, then if we sent x to minus x, that would leave us with minus d of the new x, let's say x prime. So we now have that n needs to be even. And similarly, the x derivatives in the mixed partial need to be even as well. Excellent. Okay, so we're in a pretty good place. Let's start using some other things that we know in order to make our lives a little bit simpler. Really, we're kind of at the extent of what we can say just with symmetry. And now we need to start making some other assumptions. In particular, I just said we're going to assume that we want the thing that is the most local possible object, which means we want to take these operators to be sort of as small in terms of the order of the derivatives as possible. Notice that if we did that, made these as small as possible, well, we would get something that depended on the zeroth derivative, maybe, the first derivative, and possibly a second x derivative. And the mixed partials, the only thing that we could also have of order less than 2 is dt dx, but dt dx is banned because the x derivatives need to be even. So let's assume that we have something like that. The other thing is that we might multiply them together, but that's going to lead to a less local operator as well. We really want to be just adding things with some coefficients. Okay, so we'll say that a times u plus b times partial t of u plus c times partial x squared of u is equal to 0. Good. But we can actually do something here that's a little bit sneaky, which is whatever sort of we had here, like we could just pick some value and sort of send that value of u to 0. We don't really need to do that, but that is available to us. We can shift u up and down, and that doesn't change to the derivatives. So if u were not centered around 0, we could subtract out some part. Okay, good. The next thing that we want to do is make one more sort of assumption, and that is about the behavior. So this will be the last thing that we really need in order to make things work. So let's have x here and u here. And let's just draw something. So suppose that we had something like this. Now, it's basically immediately obvious what's going to happen in this situation, which is that the place where energy has sort of bunched up is going to contribute energy outwards to the sides. And notice that that place is actually defined by having a negative second derivative. So what this implies is that if a point, let's call this x naught, if u, and let me say partial x squared of u, evaluated at x equals x naught, is less than 0, then our expectation is that the partial with respect to t of u, so at this point, should also be less than 0 because it's going to go down. And notice that this should be true regardless of the actual value of the point at u, which means that we don't really need to do any of this moving u up or down, the utilization of this symmetry, precisely because it shouldn't matter in the end. It shouldn't actually affect anything. So we get that this is 0. Now we can get rid of one of those constants, and this leaves us with exactly the equation that we found before. Good. Where I've switched a few of the constants around to give us this capital D once again. Now the extensivity is going to come into play just as I said before. with giving us that D itself must be extensive. So that's really all there is to it. We made a few assumptions about what had to be the case, and we looked for the simplest differential operator that gave us everything that we wanted. It gave us the symmetries, it gave us the simple behavior that we wanted, and it was as local as possible. So again, this is just going to be a guess. It may be that in certain circumstances, this guess will fail. There'll be reasons that we need more orders in the differential equation or something of that nature. But it turns out, empirically speaking, that this is a good approximation for most of the things that we want to do. There's a possibility that we could give a more complete derivation than either of the ones that I've given here. But I think that this does pretty clearly give us a sense that this type of equation is important. Again, the thing that we really want to notice is that we have a single derivative in t, but two derivatives in x. And we'll see that this gives us really super interesting behavior when we get to the next lecture. The last thing that I want to note here, which I think might be interesting for those of you who've taken quantum mechanics, is that this actually might look eerily similar to an equation that you've spent a lot of time with, the Schrodinger equation. So again, this is the heat equation. And we can compare it to the Schrodinger equation. The Schrodinger equation would have an I out here, and possibly an h bar. I'm actually going to ignore h bar as a constant because really all that matters for determining how the behavior works is that I. So we would have something like I partial t of, in this case, it would be psi, is equal to, so if we were thinking about the free particle Schrodinger equation, it would equal some constant, let's just say c partial x squared of psi. And it turns out that even though you're probably very comfortable working with this equation, the heat equation is not that similar to the Schrodinger equation. That introduction of I here turns out to change the behavior quite a lot. Okay, one more thing actually, I should have been clear before, is that this is called the heat equation, but in fact it describes quite a lot. In the last video, in the constructive approach, I assumed that we were taking thermal joins of these different boxes in our 1D line. But there was no particular reason that I had to choose a thermal join. I could have said that all the boxes have the same temperature and pressure, and then done a chemical join between them. And in fact, if I had done specifically that case with a chemical join, and I guess the more natural situation actually would have been a chemical join at equal volume and temperature, but whatever, I still would have gotten basically the exact same behavior for now the particle number, or for the particle density in this case, would be more natural just because the number in these boxes would get very small. But in any case, if I did that, I would come up with an equation that is sometimes called Fick's law of diffusion. So the heat equation goes by many names depending on what it's describing. This is sometimes also called Fick's law. The idea is that it describes diffusion of something, meaning basically the spreading out. This process whereby the points that are high contribute whatever the medium is out to the sides, out away from the high point, is basically diffusive. So that gives a little bit of intuition about how this kind of equation works. In the next lecture, we'll do a deep dive on the heat equation. It's unfortunately less than maybe we would want to do, but we got a lot to cover in this class. I'll see you in that one. I'm super excited.